So again, we have another titration sort of example. And really a titration is a fancy way of saying really solution stoichiometry. And that's a fancy way of saying it's just a stoichiometry problem, right? So we're going to follow our steps here. So again, in this case, we are not given any reaction. So that is always the place where you want to start. Remember, always want the proper formulas first, and then we want to balance. So we got sodium hydroxide, which should be NaOH. Sulfuric acid is H2SO4. Remember that we talked about that acid and base reactions are really just double displacement reactions. So whenever you have the acid base, you are going to create water, which is our H2O. And that comes really from the acid and the base. The H from the acid, the OH from the base. The salt's going to be the other thing made. And remember, sodium is +1, sulfate's -2, which means Na2SO4 would again be the proper formula. So remember that none of this is going to work correctly if you do not get the right formulas down first, and then you want to balance. So that's some balancing there. Let's go with a 2 there and a 2 there. I'm going to hope for the best. I did that really quick, but I'm going to hope for the best there. I think it's right. So let's take then look at what we got going on in terms of information. We're looking for the volume of sodium hydroxide. We do have the molarity, 0.355. Remember, I'm going to turn that into moles per liter since I want to see both units. We also have the volume here of H2SO4, and we have the molarity of it as well, 0.5. And I'm going to again turn it into both units. So once again, we can hopefully see this is not a limiting reagent problem. We don't have the way to get the moles for everybody, but we do have the way to get some moles to this guy. So this is again a basic stoichiometry problem. When we think about the molarity for our sodium hydroxide, once again, that's moles per liter. We're looking for the liters. We have the molarity. Remember, we're going to use stoichiometry to get the moles of the sodium hydroxide so we can actually calculate it. So we're ready to really start our calculation. We're going to go with our volume converted into liters of our H2SO4. So that will give us 0.125 liters, dividing our, I feel like it didn't show up on the screen. I feel like I wrote it. There it is. That was a dramatic pause right there as well. All right, so we got 0.125 liters, which again is our 125 converted to liters. Using our molarity here with both units, we're going to multiply by it. And that's going to give us our moles of sulfuric acid, which is 0.125 times 0.5. 0.0625 moles of sulfuric acid. As we talked about previously, we're not interested in sulfuric acid. We are interested in the sodium hydroxide. So this is where our third step comes into play so that we could go from moles of sulfuric acid to moles of sodium hydroxide. In this case, from the equation, it is a 2-to-1 relationship. So not a 1-to-1 like we've been seeing. So here we're going to go with 1 mole of sodium H2SO4. I'll write that right. And that gives us 2 moles of sodium hydroxide. The moles of sodium hydroxide are going to cancel, and we'll end up with 0.125 moles of sodium hydroxide in this case. First off, any questions on that there? This again is our stoichiometry part. Balance the equation, convert to moles, mole to mole relationship. The fourth step here is we're now going to use the moles we just calculated and the molarity that we just calculated to figure out the volume. So using our moles of our sodium hydroxide and also the molarity of our sodium hydroxide as a conversion factor, so we can flip this around and use it the other way. Liters on top moles on the bottom from the molarity. The moles will then cancel in this case. Again, because this is set up stoichiometry way, dimensional analysis way, we know we're going to divide what's on the bottom, and that's going to give us 0.352 liters, which if I wanted it in milliliters, 1 liter would be 1,000 milliliters. That's going to give me 352 milliliters of sodium hydroxide in this case. Again, this would be basically our fourth step there. So again, hopefully you can see a pattern. Stoichiometry is really, our titration problems are really just solution stoichiometry problems, same four steps. I would say probably a 99 times out of 100, it's going to be just a basic stoichiometry problem. You probably won't hit too much limiting reagent type situations with this type of question. Not a whole ways, yeah. Truthfully, in this question, because I didn't specify it, you could have left it in liters or you could have left it in milliliters. It would have been fine. Obviously, if it said milliliters, you should go that way. Or if it says liters, you should leave it in liters. Other questions on that one there? All right, let's try another one here. One last titration problem. If a titration requires 63.5 milliliters of 0.375 molar calcium hydroxide to reach the equivalence point of 95.5 milliliters of hydrobromic acid, what is the molarity of hydrobromic acid? And just a side note on the previous problem, like we were talking about in lecture, you could not use M1 V1 equals M2 V2 because again, it was not a one-to-one relationship, so you would have been off. So again, you should work it out this way and don't take that shortcut because they say you take a shortcut, you get lost sometimes. Yeah, so you don't want to get lost. All right, give this one a go here and then we'll go over it. Okay, let's take a look. Again, we're going to need an equation. We're doing a titration. The equivalence point is basically the end of the titration or the reaction. So remember, calcium hydroxide, calcium is +2, hydroxide's -1. So that's a CaOH2. Hydrobromic acid is HBr. Again, going to basically make water in a little double displacement reaction here. So the calcium again is +2 and the Br is -1, which means you should end up with CaBr2. Now again that we have all the correct formulas, we're going to do some balancing here and a 2 there and maybe a 2 there as well. Again, I feel like I'm just throwing 2's up there, but we'll go that way. In this case, we want to look and see what we got going on. We got calcium hydroxide, 63.5 milliliters. We have the molarity of it, 0.375 moles per liter. For our HBr, we're actually have the volume here, 95.5 milliliters. And we are actually looking for the molarity in this case. So in this particular problem, we can only get moles here, which tells us, again, it's a limiting reagent. Remember, for our molarity, which is moles per liter, we do have the liters part for the HBr. We will need the moles part. And again, that's where the stoichiometry is going to come into play. We're going to be able to get the moles part of it from the stoichiometry. So we'll start with our one that we can convert to moles, which is over here. Once again, always into liters when we're using molarity by itself. So divide by 1,000. Going to multiply it by the molarity there, not molar mass, but the molarity. I'll spit that out maybe. Calcium hydroxide. Liters are going to cancel. That is going to get us 0.0635 times 0.375. 0.0238 moles of calcium hydroxide. Once again, we're not interested in calcium hydroxide, but HBr. So this is really the stoichiometry part of the move here to go from our calcium hydroxide to our HBr. It is a 1-to-2 relationship. So we will go with that. 1 mole of calcium hydroxide gives me 2 moles of HBr. that is going to go away there and give us 0.0476 moles of HBr. This again is still our equation, convert to moles, mole to mole relationship. So again, the same 3 steps as all the stoichiometry problems we've done. The difference here though is we now have the moles part that we needed, and we already have the liters, so we're good to go to figure out the molarity here of our HBr. Would be the moles we just calculated, divided by our volume, which again, we do need to convert to liters, so we need to divide it by 1,000, 0.0955 liters. That's going to get us here a molarity of 0.499. This is going to be moles per liter as none of the units cancel of HBr. R at this point, since it is the end of the calculation, you can put the big M instead and do HBr. They're both perfectly acceptable answers. And again, this would be basically our 4th step in our stoichiometry calculation. Any questions on that one there? So you can see these are really the 3 sort of very common endings for solution stoichiometry. We could get grams like some of the examples we did earlier. We could get volume like we did, and we could also calculate the molarity of it. Any questions on any of that there? All right, that wraps up chapter 15. So the next chapter, which is the second to last chapter, yay. No, I'm just kidding. But yes, is on acid and bases and clear. We just did the experiment on it. So let's talk a little bit about it officially here. So we're all on the same page, hopefully. So as I mentioned before, acids were first recognized by sour taste. Vinegar is acetic acid like you use in today's lab. Lemons have citric acid. Bases are characterized by a bitter taste. Obviously, you shouldn't taste any acid or bases in lab. They do feel very slippery. A lot of soaps, kind of like Drano, that type of stuff, those are all basic type of solutions. Now, bases are sometimes referred to as being alkalis, or the word alkaline is sometimes used to refer to being basic. And as we will talk about, a lot of our strong bases are found from group 1 and 2 on the periodic table. Group 1, right, is the alkali metals, right? And group 2 is the alkaline earth metals. And that is where a lot of our strong bases actually come from. If you hook up OH with anybody in group 1 and group 2, pretty much you're going to have a strong base. And those are things like sodium hydroxide, potassium hydroxide, and so forth. Now, Arrhenius was the first person that sort of understood and did work with acid and bases. And the Arrhenius definition, or the basic definition of an acid, is something that has the ability to produce H plus ions in solution. And as I mentioned earlier, what we're talking about here is free floating H plus ions. They're not attached to anything. They're just freely floating around basically by themselves. Another really important sort of relationship, as I mentioned as we were doing the lab, is for acid and base chemistry, H plus and H3O plus, which is the hydronium ion, are interchangeable. They basically mean the same thing. They are interchangeable in formulas. They're also interchangeable in equations or reactions. They basically mean the acid part of the solution is the hydronium ion. They basically mean the same thing. Now, a base, as it says up there, is something that can produce OH minus or hydroxide ions in solution. And it's the same idea when we talk about hydroxide. We're talking about the ability to produce free floating OH minus in solution, not attached to anything, just freely floating around by itself, having a little swim in the summertime. Yes. And again, that as we will talk about, the relationship or proportion of H plus to OH minus that you have in the solution will determine whether or not the solution is acidic, basic, or really even neutral. And that sort of relationship is really important. So let's talk a little bit about how we get there. If we take something like hydrogen chloride gas and we add it and dissolve it in water, we will get hydrochloric acid. If you remember when we talked about naming acids, acids will typically have the AQ symbol next to them. And that means that they are dissolved in a solution and they will break apart. Sodium hydroxide dissolved in water will make sodium hydroxide, which again will break apart. Strong acids and strong bases are strong electrolytes. They will completely break apart in solution and not stay together. Now, this definition of an acid and base was a really good starting point in terms of acid-base chemistry, but a lot of times he did work with bases that had hydroxide in them. And a lot of strong bases will have hydroxide in them, but not all bases need to actually have hydroxide in them. So something like sodium hydroxide is a strong base because when it goes for a swim in water, it's going to 100% break apart into sodium ions and hydroxide ions. So if you took sodium hydroxide and you dumped it in there, what you're going to do is create a bunch of sodium ions, but more importantly, you're going to create a lot of hydroxide ions really quickly because all it has to do is go into that solution. It's going to break apart. You produce a lot of hydroxide, and that's going to make the solution really basic. Now, you could have a base like ammonia that maybe you played with today, which is actually a base. Ammonia will actually react with water and it will produce NH4 plus and OH minus, or ammonium hydroxide. And this is still considered a base because it has the ability to produce hydroxide, but ammonia is actually a weak base because in order for it to do it, it's got to go find water and do a little reaction to do it. Sodium hydroxide, on the other hand, doesn't have to do much other than go for a swim and it will produce hydroxide. It doesn't have to do any type of reaction. Ammonia is actually a weak electrolyte, which makes it a weak base. So not all bases will have hydroxide sort of on them, if you will. A lot of your strong bases, like I mentioned before, will. If you look at group one, if you start with lithium, sodium, potassium, and then hang a right-hand turn to calcium, strontium, and barium, if you put any of those guys with hydroxide, pretty much they're going to be strong bases. And they have the hydroxide, so all they have to do is go into the solution. They're going to release the hydroxide, and it's going to make it a really strong base. Like I said before, ammonia here has to go and do a little reaction to produce that hydroxide, and it's a much weaker base, but because it's still able to produce hydroxide, it's still considered a base in this case. So one of the sort of more general definition of an acid and a base is what is sometimes referred to as the Bronsted Lowry definition of an acid and a base. And a Bronsted Lowry definition of acid and a base, a acid is a proton donor. That is somebody that will give away a proton. What is a proton? A proton is an H plus. And that is because hydrogen has one proton, it has one electron, and it does not have a neutron. So the only way you become positive is to lose an electron, which in the case of hydrogen leaves it just a proton, which is why it's referred to as a proton. So acid-base chemistry can be a little confusing because sometimes people talk about protons, sometimes they talk about the hydronium ion, and sometimes they talk about the hydrogen. And again, they're all really referring to an acid. And again, it's just some different sort of ideas of what classifies something as an acid. Now, a base is a proton acceptor, which means it is something that will accept the H plus. And it's really important, the positive part of it. And that's where people really screw up a lot on, which is they get the idea of the H comes on or comes off, but the positive charge does affect the charge of what is left. So for example, if we take the one we just looked at, NH3 plus some water, get rid of that again, and that makes NH4 plus and OH minus. What is happening in this particular case is our NH3 is our base, which means it's going to accept an H plus over to this side. When it does, it actually creates a partner on the other side of the arrow that's related to it. And that would be this guy right here. It is related to it. It is what is known as its conjugate base. I'm sorry, conjugate acid. Now, when water loses its H plus, it makes a partner on the other side, which is actually the OH minus. And the water in this case is actually acting as the acid. It is the thing donating its H plus to the OH minus, which would be its conjugate base in this case. The absolutely only difference between an acid and its conjugate base or a base and its conjugate acid is this difference right here. 1 H plus difference. That can be the only difference that's present. When you go from a base to an acid, because it accepts an H plus, it has one more H plus when you do that. When you go from an acid to the conjugate base, it has one less H plus. Now, earlier I was talking about the positive being really important here, and this is why. When you start with something like this guy, which is neutral, and it loses a positive, I'm sorry, it actually gains a positive in this case. So this guy, which is neutral, is going to gain a positive charge. He becomes one more positively charged. So that is NH4 plus because it gained a hydrogen and it also gained the positive charge. Now, when something like water loses its hydrogen, it started with no charge. When you lose a proton, which is positively charged, you now have more electrons than protons. You actually become one more negative over here. So the charges change as you go from base to conjugate acid or acid to conjugate base. Any questions on that there? By the way, the acid and base, regular old run-of-the-mill acid and bases, are found always on the reactant side, left-hand side of the arrow. All your conjugate partners, conjugate acids, conjugate bases, are found on the right-hand side of the arrow, your product side. Now, just to illustrate this with, for example, water, not water, but hydrochloric acid. If I take hydrochloric acid, which is a strong acid, and I basically to have it in water, I could put water in my reaction here. And when I do so, this is my acid. And in this particular case, my water is going to act as my base. And the acid is going to donate over the H plus. When it does so, the water will gain that H plus and become H3O plus here. Again, gains the hydrogen and also the positive charge. The HCl loses the hydrogen and becomes one more negative here because it was neutral to start with. This over here is my acid. This would be my conjugate base. This would be my base. This guy here would be my conjugate acid in this case, yeah? Now, in this case, water is acting as a base. Water was acting as a acid in the first one, right? And things that can act as an acid or base are what are known as amphoteric. An amphoteric substance is a substance like water that has the ability to act as an acid or a base in this case. First off, any questions on that there? Yeah. Yeah. It really doesn't in this case when you're kind of thinking about acid and bases. It's there is a reaction, but it's not a reaction like you're thinking. So this is really more like you're dissolving this in solution, and that's what you're going to have in your solution. So you should think of it more in this case as more like a Bronsted Lowry definition, where we're having somebody's going to give away an H plus, and somebody's going to accept an H plus. Yeah. Now the reason I say this is not a reaction, even though technically it kind of is, but it's not, is because if you take the bottom one here, and basically this bottom reaction is just saying I put some hydrochloric acid in a beaker, basically. I'm not really reacting with like sodium hydroxide or anything like that. I'm just like have a beaker of hydrochloric acid. You could also show that by just writing HCl, because it's a strong electrolyte, will break apart into H plus and Cl minus. And this is really what's happening, is what's known as the dissociation of this acid is basically breaking apart in solution. It's not really necessarily reacting with anybody. This is also why I said earlier, what two things are basically the same? H plus and H3O plus. And the reason you get H3O plus is it is perfectly acceptable in how people are taught these days to use water as part of it, basically to show that you're kind of dissolving it in water. And when you do that, you will produce H3O plus through sort of the Bronsted Lowry definition. Here, if you don't use the H2O, you actually will just show it breaking apart more like it's a strong electrolyte sort of example, and it will break apart 100% of the time. And that's why basically both of these guys are exactly the same. Both of these reactions actually are showing the exact same thing happening. They're both showing that HCl basically went for a swim and in water basically and broke apart basically into those two things. And so you can see it's not really reacting with nothing necessarily in this particular case. But a lot of times if you do include the acid in your equation, which they kind of teach nowadays in books, you will get that H3O plus on the back end. But it's perfectly acceptable just to show something like this breaking apart in terms of an acid dissociating in a solution. Yeah. Other questions? Or, yeah. Yeah, amphoteric is a substance that can act as an acid or a base. So water in this example, in certain cases, can act as an acid or base. As we will see, there are several things that have that ability to act as an acid and base. And a lot of things, for example, like that has a hydrogen and a negative charge, it can act as an acid or base because it does have the hydrogen to give, but it also has the hydrogen. It could actually accept the hydrogen as well because it has a negative charge. So something like bicarbonate could actually work as an acid or a base. Even bisulfate, some of those polyatomic ions that look like that, they have the ability to act as an acid or base because, again, they have the hydrogen to give, and they also have the hydrogen to accept. Question on that there. So that is the consequence of the Bronsted Lowry definition, which is you do create partners that are related to each other. And again, the most important thing about that relationship is that can be the absolute only difference between them. So if you have something that there is a difference of more than one H plus, they are not related to each other in that sense. For example, like our buffer that we use today, acetic acid and acetate, which basically comes from sodium acetate. The only difference between these two guys is that one H plus, and that is why they are related to each other. Now you may be asking, it said sodium acetate. The sodium is really just a spectator ion there. It's not really doing anything. It's the presence of the acetate and the acetic acid that are partners basically here. So sometimes you will have, for example, a sodium, a lithium, something like that, a potassium hanging out there. But again, that's what you kind of want to look at is that relationship here. This would be basically, once again, a weak acid and its conjugate base. Any questions on that there? Yeah. All right, so those were the examples we just did on the previous page there. All right. So we're gonna actually lay it up there and talk about a few things here. I think since